All right, one of our main applications in the exponential section is to an economics concept called compound interest. So I know you've seen this formula before, but let's make sure that everyone knows what the kind of letters all represent. So we start with P amount of dollars, P dollars, deposited in an account at an annual interest rate of R for rate, and this has to be in decimal form. Then we can calculate the balance A depending on the number of times that the interest is compounded. So let's review what this compounded means here. So this is really a fancy word that just means the number of times per year that your interest is added on, and your balance will then be recalculated. And it's worth noting here that actually the T here has to be in years. Okay, so if you are looking at an account that is compounded annually, then your N would be 1, because that means once a year this your balance gets recalculated and your interest gets re-added on. If you're looking at something that is weekly, right, that would be like 52, right, 52 weeks in a year. So this N is just, it just represents that. P is sometimes called the principal amount. And it is just your initial amount here. So let's see how this works, like how we can use this equation here. I know there's no e's, but something's going to happen, and we're going to kind of discover the number e here. So just suppose, this is a silly example, but suppose that you are investing $1 at an annual interest rate of 100%, and you're only going to do this for 1 year. So you're just putting in $1, annual interest rate of 100%. And let's take a look and see what happens if you have some various compoundings here. So we're looking for how much money will you have. So we're looking for this amount A, the balance. Our principal is going to be 1, and the rate here will be 100%. Okay, so we've got A equals 1 is our principal. Our rate here is 100%, so this will be as a decimal. If it's annual, right, this means that N is equal to 1. So we'll put a 1 in place of N. And we're doing this for 1 year. So that means that T here is equal to 1 in all of these examples. So we'll get 1 times 1 up in the exponent. Okay, so 1, there's a lot of 1s in here, but inside these parentheses, we have 1 plus 1, which is 2. 1 times 2 to the first, so that's $2. So that's how much we would have if it was compounded annually. Makes sense, 100%, right? That means we'll double our $1. Okay, let's see if we compound monthly. So this would mean 12 months in a year, so N is 12. Okay, so we'll have our principal is 1 still. We just have a 1 in the formula. The interest rate is still 100%. Now the N is 12. So we'll have a 12 in the bottom there, and then we'll have 12 times, and the amount of time here, the length of time is still 1, so it'll be 12 times 1. Now, if you calculate this out, you get about $2.61. Okay, so right away, more compoundings is better, right? The more often your interest gets re-added on, the better it is for you, right? We have an additional 61 cents to go have some fun with. If instead we are doing daily, okay, so this is even more compoundings, right? This would be 365 for our N value. Well, everything here, right, principal will just be 1. We'll have 1 plus 1 over 365. And then in our exponent, we'll have 365, and our time length is still 1. So we'll have 365 times 1. So calculating this out, we get about $2.71. So it's an extra 10 cents from before, just to calculate every day instead of every month. Okay, so maybe you can see this pattern right more and more. Let's see if we can compound every minute. All right, so what does that mean N is equal to? Well, there's 60 minutes in an hour, there's 24 hours in a day, and then there's 365 days in a year. So this comes out to be 525,600. All right, that's how many minutes are in 1 year. So if we do, again, the balance here will be our principal, which is still $1. We'll have 1 plus 1 over 525,600. Then we will raise that to the 525,600, and again, 1 year, so times 1. Now, if we calculate this, we get about 2.71828, and it keeps on going, but we'll say 2.72 because this is money. But 2.71828, right, that is approximately our number E, right? So if you look at more decimals, it's actually very, very close. So the reason that I'm showing this to you is because, right, what that limit that I described to you in the beginning of this video is actually kind of what we're doing here. Like, we're letting this n go to infinity. It's not too close yet, but it's pretty big. And when we do that, when we compound more and more and more, right, every second, every millisecond, every single instant, then what we get is something called continuous compounding. And part of this formula here is just going to become E instead of having all of this fractions with R and N and everything involved. Okay, now there's a little bit of kind of rearranging to do here. It's not too important. The idea here, right, just as continuous compounding, right, every minute, every second, the more and more we compound our formula, this E is going to pop up in it. And it actually becomes A equals P, principal stays there. But this part here, we can, again, rearrange it a little and we'll get E to the RT. Okay, so to summarize the different formulas that we have here, well, for compound interest, there are basically two kinds. We can compound our balance n times per year, and the formula for that is just the one we were talking about, where we've got A, which is the amount in the account or the balance, equals the principal times 1 plus the interest rate annually over the number of compoundings, and then that's raised to the n times t, where t is in years. When we compound continuously, we still have A for our balance, we still have P for our principal or our initial amount, and then as we just saw, E pops up and we just get E to the RT. So there's no ends because, again, that is essentially infinity, and we have this PERT formula. Here's just a graphical representation of the difference between different compoundings. When we compound, for example, yearly, and these are all starting with an initial amount here of 1,000, so this is our P value, our principal. Then after 1 year, so the green is yearly, after 1 year here, then our balance is increased at that time because that's when our interest is added on. And then every year we see this jump because our balance, right, is increasing, but only at the end of each year. If we compound more often quarterly, so that's 4 times a year, that's in the, it's really hard to see here, but the yellow maybe out here is a little bit easier, right? So 4 times in 1 year, our balance jumps up. And then we get more and more interest in our account or maybe in our loan because we have more in there to gain. If you compound monthly, that's this pink jagged one here, right? There should be 12 of these jumps in 1 year. And then if we compound continuously, we get this nice sort of like smooth curve, right? Because it's essentially happening at every second. And so this curve is made up of just infinitely many little jagged points there. We can see that the continuous compounding actually tends to be better, right? This one has the most, it's above all of the other kinds of compounding. So here's an example where we can calculate some things with different interest rates and some different compoundings. So suppose that you're creating a trust fund for your newborn nephew because you're very generous. You deposit just $12,000 that you got laying around in an account, and you say that you're going to turn this over to your nephew on their 25th birthday. And you have these 4 different options. We have option A, which is 7% interest compounded continuously. We've got option B, which is 7% compounded quarterly. And then in C and D, we both have 11%, one continuous and one quarterly. Okay, so this is just an exercise in kind of using these formulas and calculating, things with them. But also let's see, what comes out of this and what's better, basically. Okay, so the continuous compounding, right? This is an important word. This means that we're going to be using the PERT formula, A equals PE to the RT. And our initial amount, the principal, right, is 12,000. And the interest rate in this example is 7%. So we're going to put that as 0.07. And we're doing this on their 25th birthday, right? That's what they would essentially gain. So we're going to put in 25 for T. Right, just if you're a little confused where that's coming from, here we've got this is T, this is time, right? This is our initial amount P, this is R, but we've got to convert that to a decimal. Now, if we calculate this, we get about $69,055.23. A very generous 25th birthday. I bet you wish your aunt or uncle may have done that for you. So let's see what this would look like if we were compounded quarterly. Okay, so in this case, we're going to be using our other formula, right? It's not continuous compounding, so our other formula has the n in there. And the n, because it's quarterly, right, that means that n will be 4 times per year. Our principal is still 12,000. We'll have 1 plus our interest rate of 0.07, and then n is 4. And in our exponent, we've got n times t, so that'll be 4 times 25. And if we calculate that out, we get something that's not as good. We get $68,017.87. Okay, so even with the same interest rate, the continuous compounding, just like in the graph that I just showed you, is better than non-continuous compounding. Okay, so you might be guessing then that C is probably going to be our winner here, right? Because a larger interest rate would be even better. But let's calculate that, right? So here, this is continuous again. So we're going to be using our PERT formula, but now instead of 0.07, as in option A, we're going to have 0.11. And that'll still be times 25 years. All right, so in this case, we have a whopping $187,711.58 just from $12,000. Although 11% interest rate is insanely high, but if you took out on the opposite end a loan for $12,000 and you waited 25 years and just let it sit there, you would end up paying this amount if your interest was 11%, which, this can go both ways here. Okay, so let's see option D. We've got our last one here, compounded quarterly, which again is n equals 4. And so we'll substitute in here, we'll get using this formula. Right now our R here is going to be different, although our n will still be 4. So we'll have 1 plus 0.11 over 4 to the n, which is 4, again, times 25. Right, in this case, we get about $180,869.07. Okay, so this example, I just wanted to illustrate, obviously, right, you choose option C. This is the best choice here. But continuous compounding does tend to grow faster. And of course, a higher interest rate does grow faster as well. So we can see in this graph here, it's just got two examples here. We have, these are just the continuous compoundings. And even though they start off like after 5 years, they're not too far apart. But if you let it go for a while, right, this growth is much larger after 25 years, right? This difference is enormous. We've got 187,000 and 69,000. That's more than double. Okay, so we also have this example can help us to see that the growth rate or the percent growth here, right, does make a difference, right? This is kind of what is increasing our graph faster. And so we can kind of generalize this, right? Even though that the 12,000 here was our initial amount, the difference in the number that is multiplied by the t, right, which in the one case is 0.11, looking on the graph here, and the other case is 0.07, right? That is actually called the growth rate. And this is one reason why the natural exponential function is really nice in the way that we write it, because that growth rate, that number that's multiplied by the t, it's really easy to read off of the formula. right? We can read off the initial value really easily. And then if we keep everything to have base e, we can easily compare different exponential functions in a way that would be a little harder if we had different bases. Okay, so in fact, every exponential function can be rewritten in base e, which is another reason why e and the natural exponential functions, why they're great and why we like to use them a lot.